will now discuss set equivalences. There are going to be 4 ways to show set equivalence: a paragraph proof, a logical equivalence, a membership table, and a Venn diagram. So we'll start with the paragraph proof. If A and B are sets, we want to show that A intersect B union A intersect B bar is equal to A. So we'll start with the paragraph proof. And the idea is to start with letting X be an element in the left-hand side. So we're going to let X be an element of A intersect B union A intersect B bar. By definition of the union, this means X is either in A intersect B or X is in A intersect B bar. Let's suppose it's in A intersect B. Then, by definition of the intersection, it's in both A and B. If we do the other case, supposing it's in A intersect B bar, then X is in A and X is in B bar. And you'll notice either case, we have that X is in A. So, since we had an element in the left-hand side, and we showed that it's also in the right-hand side, we've shown that A intersect B union A intersect B bar is a subset of A. For the second part of this proof, we have to do this same thing going the other direction. So we'll let X be in A. We don't know if X is in B or not, so it's either in B or it's not in B. If it's in B, then X will be in both A and B, so it'll be in A intersect B. If X is not in B, then it'll be in B bar, so X is in A intersect B bar. So it's either in A intersect B or it's in A intersect B bar. So if I take the union of these two, X is guaranteed to be in there. So now we've shown that A is a subset of A intersect B union A intersect B bar. And this shows that the two sets are equal. So for a paragraph proof, you let X be an element in one side, show it has to be contained in the other side, and then you switch. For set identities, there are several of the identities. So your identity laws, A intersect U is equal to A, and A union empty set is equal to A. Our domination laws, A union U is equal to U, A intersect the empty set is equal to the empty set. Idempotent laws, A union A is equal to A intersect A is equal to A. Our double complement, so A bar bar is just A. Commutative laws, A union B is equal to B union A, and then A intersect B is equal to B intersect A. We have the associative laws. So this says wherever our parentheses are, doesn't matter as long as we're doing all unions or all intersections. Distributive laws, A union B intersect C is equal to A union B intersect A union C. And then A intersect B union C is equal to A intersect B union A intersect C. We also have De Morgan's laws. A union B bar is equal to A bar intersect B bar, and then A intersect B bar is equal to A bar union B bar. So if we're taking a complement of an entire thing, we have to switch intersection to union and union to intersection. The absorption laws, A intersect A union B is equal to A, and A union A intersect B is equal to A. And then finally your complement laws. A union A bar is equal to U, and A intersect A bar is equal to the empty set. So now let's do these showing logical equivalence. So we always start with one side of the equation, which is what we're given. From here, we can use our distributive law to kind of pull out the A. We have A intersect B union B bar. Our complement law said that A union A bar is equal to U, so in this case B union B bar is equal to U. Then the identity law said that A intersect U is equal to A. So we started on the left-hand side and we made it to the right-hand side. So these are equivalent. We can also use membership tables. So membership tables are going to be very similar to truth tables. We set it up, and this time we use ones and zeros. 1 indicates that the element is in there. 0 indicates that it's not. So for A intersect B, we need it to be in both A and B. So that only happens in the first row. B bar, this will switch ones and zeros. And then A intersect B bar. We need it to be in both A and in B bar. So we need a 1 in both rows. So here and here. And then union indicates we just need a 1 in one of these two columns. And we can see that this is actually equal to our A column. Finally, Venn diagrams. So I'm going to build the Venn diagram for the left-hand side. Here's A intersect B. It's what they have in common. We also have to deal with A intersect B bar. So that's everything in A that's not in B. And then we want to take the union of this Venn diagram and this other one to get this new one. And we can see that we have just shaded A. Therefore, these are equal.